In Euclidean geometry, a kite is a quadrilateral whose four sides can be grouped into two pairs of equal length sides that are adjacent to each other. In contrast, a parallelogram also has two pairs of equal length sides, but they are opposite to each other rather than adjacent. Kite quadrilaterals are named for the wind-blown, flying kites, which often have this shape and which are in turn named for a bird. Kites are also known as deltoids, but the word deltoid may also refer to a deltoid curve, an unrelated geometric object. A kite, as defined above, may be either convex or concave, but the word kite is often restricted to the convex variety. A concave kite is sometimes called a dart or arrowhead, and is a type of pseudo-triangle. Special cases: if all four sides of a kite have the same length, it must be a rhombus. If a kite is equiangular, meaning that all four of its angles are equal, then it must also be equilateral and thus a square. A kite with three equal 108 degrees angles and one 36 degrees angle forms the convex hull of the lute of Pythagoras. The kites that are also cyclic quadrilaterals are exactly the ones formed from two congruent right triangles. That is, for these kites the two equal angles on opposite sides of the symmetry axis are each 90 degrees. These shapes are called right kites, and they are in fact bicentric quadrilaterals. Among all the bicentric quadrilaterals with a given two circle radii, the one with maximum area is a right kite. There are only 8 polygons that can tile the plane in such a way that reflecting any tile across any one of its edges produces another tile. One of them is a right kite, with 60 degrees, 90 degrees, and 120 degrees angles. The tiling that it produces by its reflections is the deltoidal trihexagonal tiling. Among all quadrilaterals, the shape that has the greatest ratio of its perimeter to its diameter is an equidiagonal kite with angles pi 3, 5 pi 12, 5 pi 6, 5 pi 12. Its four vertices lie at the three corners and one of the side midpoints of the Reulo triangle. In non-Euclidean geometry, a lambic quadrilateral is a right kite with three right angles. Characterisations: a quadrilateral is a kite if and only if any one of the following conditions is true. Two disjoint pairs of adjacent sides are equal. One diagonal is the perpendicular bisector of the other diagonal. One diagonal is a line of symmetry. One diagonal bisects a pair of opposite angles. Symmetry: the kites are the quadrilaterals that have an axis of symmetry along one of their diagonals. Any non-self-crossing quadrilateral that has an axis of symmetry must be either a kite or an isosceles trapezoid. These include as special cases the rhombus and the rectangle respectively, which have two axes of symmetry each, and the square, which is both a kite and an isosceles trapezoid and has four axes of symmetry. If crossings are allowed, the list of quadrilaterals with axes of symmetry must be expanded to also include the antiparallelograms. Basic properties: every kite is orthodiagonal, meaning that its two diagonals are at right angles to each other. Moreover, one of the two diagonals is the perpendicular bisector of the other, and is also the angle bisector of the two angles it meets. One of the two diagonals of a convex kite divides it into two isosceles triangles, the other divides the kite into two congruent triangles. The two interior angles of a kite that are on opposite sides of the symmetry axis are equal. Area: as is true more generally for any orthodiagonal quadrilateral, the area A of a kite may be calculated as half the product of the lengths of the diagonals P and Q. Alternatively, if A and B are the lengths of two unequal sides, and theta is the angle between unequal sides, then the area is tangent circles. Every convex kite has an inscribed circle, that is, there exists a circle that is tangent to all four sides. Therefore, every convex kite is a tangential quadrilateral. Additionally, if a convex kite is not a rhombus, there is another circle outside the kite. tangent to the lines that pass through its four sides. Therefore, every convex kite that is not a rhombus is an ex-tangential quadrilateral. For every concave kite there exist two circles tangent to all four sides. One is interior to the kite and touches the two sides opposite from the concave angle, while the other circle is exterior to the kite and touches the kite on the two edges incident to the concave angle. Dual properties. Kites and isosceles trapezoids are dual. The polar figure of a kite is an isosceles trapezoid, and vice versa. The side-angle duality of kites and isosceles trapezoids are compared in the table below. Tilings and Polyhedra. All kites tile the plane by repeated inversion around the midpoints of their edges, as do more generally all quadrilaterals. A kite with angles pi 3, pi 2, 2 pi 3, pi 2 can also tile the plane by repeated reflection across its edges, the resulting tessellation. The deltoidal trihexagonal tiling superposes a tessellation of the plane by regular hexagons and isosceles triangles. The deltoidal icosahedron, deltoidal hexacontahedron, and trapezohedron are polyhedra with congruent kite-shaped facets. There are an infinite number of uniform tilings of the hyperbolic plane by kites, the simplest of which is the deltoidal triheptagonal tiling. Kites and darts in which the two isosceles triangles forming the kite have apex angles of 2 pi 5 and 4 pi 5 represent one of two sets of essential tiles. In the Penrose tiling, an aperiodic tiling of the plane discovered by mathematical physicist Roger Penrose, face transversal self-tessellation of the sphere, Euclidean plane, and hyperbolic plane with kites occurs as uniform duals. For Coxeter group PQ, with any set of PQ between 3 and infinity, as this table partially shows, up to Q equals 6. When P equals Q, the kites become rhombi. Conditions for when a tangential quadrilateral is a kite. A tangential quadrilateral is a kite if and only if any one of the following conditions is true. The area is 1/2 the product of the diagonals. The diagonals are perpendicular. The two line segments connecting opposite points of tangency have equal length. One pair of opposite tangent lengths have equal length. The B-medians have equal length. The products of opposite sides are equal. The center of the incircle lies on a line of symmetry that is also a diagonal.